Okay, so first of all, before I go into our project, I think since it's the 10th anniversary of the Center for Computational Geometry and Computational Design, I just give a few cornerstones of the facts of the center. So first of all, the vision that the center had was to perform cutting-edge research at the interface of mathematics, computer science, architecture, civil engineering, and design. So basically that's the 4 faculties we have, and all the 4 technical faculties, and link this basically to the design idea. And we also want to contribute to the education, and that's what we are doing also in this session, to show our PhD students of a new generation of bright minds in both technical as well as artistic field. So it's like a big flowery formulation, but well, who combine geometry and computational design to develop the innovations of tomorrow. I mean, I hope you can see that we try to achieve that. And so these are actually the faculties that are involved. I'm sorry if sometimes I do not list the whole name of the faculty, but the part that is actually really contributing to the center. And you see here also the names of the people who are founding members and current members of the center, right? So they overlap a lot with the people who work in our SFB. So that has kind of converged a lot. So that just you see the names of these ones here. And just a brief timeline, I mean, our vice rector has introduced basically all of this, but just so you can see it on one slide. So it was founded by Helmut in 2014. And then 2 years later, we got our first major grant, my first major funding. That was the Doctoral College on Computational Design. So we got our first influx of bigger influx of students who worked on all these topics. Then when Helmut left, finally left to Cast for good somehow, then he handed over the center to me. And 2 years later, we managed to get the grant, our first really big grant, like really also competitive grant that was competitive in whole Austria. So it was the Special Research Program, SFB, Spezialforschungsbereich, Advanced Computational Design. And you have to think that we started work on the proposal in May 2018, and we started the work of the granted proposal in March 2020. So you can see that it takes a lot of work to get such a proposal running. In the same year, because of this grant, the university recognized that we are doing a really important work here. They upgraded us from a interfaculty project thingy to a real research center. So now we are directly under the Vice Rectorate for Research, and we are our separate unit, and that's actually great also. And then this year, we got the prolongation grant. So this is also great because it allows us to continue 4 more years of work here. And as you can see, this was also a lot of work, not as much as the first one, but we started in February 2023, we started to work on the prolongation proposal, and it got through at the end of the year, and since 1st of March 2024, we are now in our second period. Yeah, and today we are celebrating 10 years of GCD. That's why we're here. And the SFB is one of the big projects, and the Doctoral College was another one. And meanwhile, also we got Christian Doppler Laboratory on Woodcomb, which is also quite a significant one, and many, many other collaborative projects between the members of the center, amounting to a lot of funding as well. Okay, so that's enough about the center. Now let's move over to the SFB. So I have to apologize a little bit about my voice. I was, for a couple of weeks, I was more or less lying in bed, and 2 days ago I had no voice at all, and I'm slowly recovering, so it's getting there. So. Okay, so now I'm very happy to give you a short overview of this project, the Advanced Computational Design project. And this is, as I already told you, funded by the Austrian Science Fund. in the SFB program, and yeah, as I also said, it was prolonged for another 4 years, starting in March. So this includes 6 sub-projects from TU Wien, and 1 each from the University of Innsbruck and TU Graz. So now after this overview, you will see details on some selected research results presented by 2 PhD students, and then by a truly interdisciplinary team of the SFB, and that will also go into the breakdown. So what is our motivation? So in this project, we want to fundamentally change the field of architecture, engineering, and construction. And this field has an enormous impact on society and the environment, as I'm sure many of you who are actually working in these fields are aware. And as we have already heard in several of these other talks, that there's these problems of sustainability, of ecology, and so on. So unfortunately, it currently lacks a lot of computational design tools to face upcoming challenges, although we have seen that many groups around the world are working on these problems. So we are too. So in particular, we live in times of extreme urban growth and limited resources. For example, Vienna, this city here, is forecast to grow by a size equivalent to the city of San Francisco in the next 30 years. Well, and there are some flagship projects that show how architecture could contribute to solving these challenges by using, for example, renewable materials like timber or biocomposites, and combining this with lightweight, you remember, construction through sophisticated geometric computations and mechanical construction. But architecture like this is not very common, and the reason is that it requires innovative design, and this in turn requires the collaboration of many different stakeholders at an early design stage. And currently this is usually too costly and difficult, and only done for flagship projects, and at enormous costs as well usually. So, and furthermore, most of these results are only prototypes, so the insights are often not reusable or generalizable because they are not based on basic research. So we wonder, why is this so expensive? Well, in 2019, we believe the reason is that there is a lack of computational tools for collaboration, especially in the early design phase, which is the most important one. In fact, if you look at the digitalization of different sectors, construction resided at the very bottom of this list, right next to agriculture and hunting. While these numbers are quite old already now, they're from 2015, nothing has fundamentally changed, as can be seen in this 2022 survey for Europe, where construction is again at the lower end of sectors regarding digitization. Therefore, this sector still faces stagnating productivity and innovation. And as a result, while we face challenges of urban growth, as I've said, and the scarcity of resources, the vast majority of AEC still uses conventional processes and standard wasteful materials, causing a huge ecological impact. So we heard that the concrete industry is responsible for 8% of carbon dioxide emission, and if you take the whole AEC industry as a whole, we saw numbers that this amounts to actually 30% or more. I mean, we have seen that you can make concrete better, and there's researchers working on that, so that's great. So for us, the obvious solution is to create digital design tools for the early design phase using the field of information and communication technology, so basically informatics, and which obviously resides on the top of this list. Such tools would allow real-time feedback and communication on design choices across different disciplines at an early stage of a project, where there's the most impact, obviously. However, the computer scientists developing these tools, they often lack domain knowledge, and that leads to suboptimal solutions. In fact, none of the big software vendors, for example, in the industry, have even tried offering such tools for the early design phase so far. At least that's I'm a computer scientist, so our friends from architecture may tell me otherwise, but that's what our friends from architecture told me. So therefore, our vision in this project is to bridge this gap between AEC and ICT in the early design phase. Wrong button, yeah. Through basic research in an inter and multidisciplinary fashion. And actually now, for already 4 years, the SFB Advanced Computational Design has been developing tools and processes for the early design phase to implement that vision, like tools that can bring disciplines together and improve the quality and efficiency of AEC. So how does this project look like? So what is that? Many big words, what we want to do, so how does it look concretely? So the work is actually in 3 primary areas. First of all, in design methodology. So in order to provide the primary interface technology to the human designers and also specialists. And we deal with the question how they input design ideas and communicate with each other, but also how to integrate the computational design tools from the different disciplines. And the second area is visual and haptic design interaction in order to provide feedback for decision support and communication at all times during the early design phase. And third, form finding, or the realization of design intents in actual objects, having geometric, kinematic, and physical properties. So roughly the first area here that I mentioned covers somehow the input design of a design project. The second one is kind of the output side, and the third one is somehow the processing or simulation side. So now, in more detail, in the area 1, we follow 2 complementary approaches of design methodology. So on the one hand, we are working on transforming implicit design intents given by sketches on 3D drawing canvases into geometric surface models. And these models then serve as explicit representation for the integration with computational tools. And more details will be presented later in this session by Sharon. On the other hand, we also look at more physical interaction to create variations of volumetric point clouds using machine learning, allowing the exploration of large and more abstract design spaces. In the area 2, visual and haptic design, at any time, the current state of the interaction is presented to the user as accurately as possible. So on the one hand, visually, through a real-time simulation of light propagation through the scene. That's our area's expertise, so I'm coming from computer graphics, and that's what my group is doing. And on the other hand, also through the haptic sense, so allowing users to experience the boundaries of an architectural space or material properties like elasticity. Going back to the visual interaction, this also works in a reverse sense, an inverse sense. By specifying desired illumination properties, the simulation can be used to calculate the required illumination setup through a novel differential light tracing method. And we will show our advances in this direction later in this session, and Lucas is going to present this. And we also extended this approach to simulate thermal radiation as well, which is also important, for example, to fight urban heat islands and so on. So in the area 3, form finding, instead of deferring complex geometrical mechanical computations to a later stage in the production pipeline, our approach is to integrate form finding already in the early design phase. For example, the possible ways a freeform surface is discretized into panels determines the feasibility, efficiency, and cost of a construction, ultimately with an impact on sustainability. In particular, later in this session, you will learn and experience how we physically realize spherical panels. But we also go beyond static surfaces and find innovative ways to transform quad-panel surfaces with applications to novel lighting and shading solutions and foldable assemblies, as you have already seen today as well. Besides geometry, we also look at the structural behavior of designs, and this is essential to introduce new green materials like so-called plant-based biocomposites. So for these materials, we developed a multi-scale model to simulate their behavior much more efficiently. And finally, we verify these theoretical results by fabricating or building them, but also experiment with completely new materials like clay or mycelium and their potential for sustainable construction. The properties of new materials are then also analyzed theoretically. And all of these projects are tightly interlinked as represented here. So to achieve all of this requires a multidisciplinary team, as you would have thought. And at the beginning of the project, we were already able to build on our GCD, as you have seen before. But then we also reached out and integrated knowledge in architectural design and material experimentation by University Innsbruck and TU Graz. So in total, the project encompasses the 4 faculties I mentioned before. So let me show you on a few examples how we work together to achieve these things. So first of all, we have created this sketching platform, and this is a central hub for all the sub-projects in the SFB. So this platform allows users to sketch in different modalities, like on an iPad or on a screen or in VR, right? And in particular, we have identified how architectural designers like to sketch using different types of strokes for boundaries and surfaces, as you will see later on. And the platform then uses these surfaces that are created from the sketching, the geometric surfaces that come out of that, to communicate with the simulation tools. For example, with the lighting simulation to compute optimal lighting conditions, or with structural simulation to compute stability for different material choices. And with geometry simulation to compute the different panelizations or tilings, or transformable variations. The platform can also convert point clouds to geometry, and all of this will be reflected in the app shown to the designer. And in certain modes, like virtual reality, the feedback will not only be visual, but also be haptic or real through fabrication. And again, 3 of these topics will be presented in more detail shortly. So putting all these different elements together, we obtain something like a material-informed design framework, which equips designers with the necessary knowledge about design implications. So starting from a sketch or physical input, the sketching platform then computes a geometric or point-based model, and this can then be interpreted by a structural analysis module for overall structural feedback, and by material models, for example, our novel model for plant-based biocomposites, which provide the mechanical input parameters. And the design can be visualized in virtual reality using realistic light simulation, and a novel origami structure positioned on a robotic arm allows for immediate feedback on the structural stiffness. So the framework also adds an important physical materialization step where prototypes of both materials and geometry are actually fabricated and presented to the user. So in summary, the overall vision of this project is to develop advanced computational design tools and processes for the early design phase, linking design methodology, visual and haptic feedback, and form finding through basic multi- and interdisciplinary research in order to improve the quality, efficiency, and most importantly, maybe nowadays, the sustainability in AEC. Thank you, and this is kind of the team of PIs in front of the Austrian Science Fund before we gave our presentations that earned us another 4 years of funding. Thank you. And now I hand over to our PhD students.
Thank you very much, Michael, for giving us an introduction to our special research topic, Advanced Computational Design. And the next presenter will be Sherwin Rasulzadeh, and he actually studied computer science first and then moved to the Faculty of Civil Engineering to conduct his research there. And he has a special interest into machine learning, so his talk will be about AI-driven ideation for 3D architectural design.
Okay.
He's actually also part of the design methodology part of the research program. So please, Sherwin.
Yeah. So, hi everyone. Welcome to my talk, AI-driven ideation for 3D architectural design. I am Sherwin Rasulzadeh, informatics PhD student from sub-project 2. So let me begin with early stage ideation. Early stage design ideation can be approached in several ways. 2 of those are sketching design and volumetric design. It is throughout this process that the architect or designer starts to ideate and bring visions to life. the time for testing options, and getting general idea of the look and feel of the design. So for now, let us focus on sketching design. In this approach, architectural design workflows are often composed of two phases. Concept design, which is often conveyed via sketching, mainly because of its low overhead in representing, exploring, and communicating geometric ideas. And the second stage is called digital modeling, where the sketch serves as a visual reference for creating and editing the geometry into desired shape. In recent years, architectural design witnessed the growing availability of 3D sketching interfaces that are often integrated with a modeling algorithm. However, many of these tools merge the concept design and digital modeling phases together, imposing often interface-specific constraints such as real-time stroke neatening or automatic stroke connection that is believed that it can disrupt the ideation process. So prioritizing the concept design first approach before modeling is the missing point of these tools. So basically what is needed is an automated geometry reconstruction pipeline tailored to 3D architectural design sketches that can capture the design intent, bridge the concept design and digital modeling phases, and takes place post the sketching phase, or also known as offline method, which has been one of our main aims in this sub-project. To this end, our solution to these criteria is a data-driven sketch analysis pipeline named Strokes to Surface, recovering curve networks from 4D architectural design sketches. We built such a pipeline upon a 3D pen on tablet sketching interface developed by my colleagues in our research group. And here you can see the interface in action. The designer has access to a set of geometric canvases, geometric primitives as canvases that can be transformed around the scene. The 3D strokes are formed by projecting drawn curves on the tablet surface to the geometry of these canvases. Additionally, temporal data of all strokes is continuously captured, providing the fourth dimension to this sketch and its constituent strokes. However, these sketches, while they are beautiful to behold and effectively perceived, they are non-trivial to transform into 3D surface models for further design communication and processing. So to do that, it has to be studied first how designers approach sketching. Our studies and observations reveal that designer-drawn strokes are mainly of two kinds: shape strokes representing edges and scribble ones suggesting presence of a surface. More to that, sketches are often imprecise, exhibiting properties such as oversketching or overshootings at junctions. Given the presence of these two types of strokes, this is similar to how curve networks are formed, where we have curve segments and cycles corresponding to surface patches. So here we can see actual use of curve networks in real-world architecture like Beijing National Stadium, also known as Bird's Nest. To proceed with our pipeline, we first collect a data set of such architectural design sketches through conducting workshops with students mainly coming from architectural education background. And then to be able to recover such curve networks from sketches, the first step would be to recognize the type of drawn strokes between the shape ones and scribble ones. To this end, using the collected data set, we manually extract a set of hand-engineered features from each stroke in each sketch. And here on the image, you can see some of these values color-coded on a sample sketch. And the feature trends among the strokes for edges compared to the ones for faces suggest the use of a classifier. So given these features, we train a binary meta-estimate or random forest classifier on them so as to recognize the type of drawn strokes between the shape ones and the scribble ones. To proceed with the pipeline and to show the individual step it takes to recover curve networks, we tried to recreate a pavilion built by University of Stuttgart in our sketching interface. And from here on, I show the individual steps on this sample sketch. As a first step, we apply the classifier, and as a result, machine gets to know which strokes are boundary ones and which are scribble ones, here shown in blue and red colors. Then, taking the strokes classified as shape, we are left with the strokes that may still exhibit oversketching. Therefore, there is the need to parse them into groups representing individual edges of the geometry. To do that, we compute pairwise similarity scores through a custom-defined scoring function. We feed them into DB-scan model. And as a result, what we get is the output shown on the right, which individual curves are representing each single edge of the desired geometry. Unfortunately, these curves are still disconnected and cannot be used for reconstruction. So given the endpoints and the tangent directions, we formulate pairwise optimization problems to fix the connectivities between the curves, resulting on a well-connected curve network on the right. So now we have the curve segments in our curve network, but we still do not know which areas should bound patches and which areas should remain empty. To detect the cycles, we can leverage the information encoded in the scribble strokes by parsing them into groups representing faces of the geometry. But since scribbles can also exhibit oversketching, we devise another scoring function, compute the pairwise similarity scores, and feed it into another DB-scan model. And as the output, we get this nice, well-segmented geometry, scribble strokes shown on the right-hand side, with each group ideally representing a specific cycle in our geometry, in our desired geometry. Then, as one last step, in order to detect the cycles, we use the bounding box of each cluster to search for them globally, and we simply detect the boundary strokes falling into each bounding box and apply existing cycle discovery methods and triangulate the cycles, resulting in a surface mesh shown on the right. To recap, here we can see stepwise outputs of the pipeline on one of our most complex sketches in terms of number of strokes. This one has approximately 400 strokes. We first, using our trained classifier, try to recognize the type of drawn strokes. Using the first clustering model, we parse the strokes into edges. And using the second clustering model, we segment the scribble strokes into surface patches. We fix the pairwise connectivities between the curves, obtaining a set of well-connected curve networks, and using the scribble clusters, we reconstruct the final surface mesh geometry. So this was briefly how we address sketch reconstruction methods, sketch reconstruction from the sketches created in our the interface MR Sketch. But as I mentioned in the beginning of my presentation, sketching is not the only way to design. We also have volumetric design, which is also called massing design. For many architects, it's the first and most critical step for building design. The process starts with quickly constructing coarse volumetric shapes within a valid design space, followed by gradually developing all the geometric detail needed for the exterior, facade, and interior design. And here we can see an example of a building designed with this method and built, dwelling at Maitrey by Odos Architects. And however, creating a good volumetric design requires numerous revisions and adjustments. Therefore, an efficient generative pipeline to assist the architects with the ideation and modeling should meet several criteria. First, it should be scale consistent to preserve the coherence between the building elements. Further, the synthesized model should exhibit both interior and exterior, and it should also enable flexible and interactive use and refinement. And the pipeline should not be able to assist only with the generation of new models, to help with more easily exploring design space, but also support the design with further geometric detailization. So our solution to this criteria is a generative data-driven pipeline named autocomplete architecture, learning to generate 3D volumetric houses with transformer networks, which has been a joint project with sub-project 3 from University of Innsbruck. So we base our approach on a data set collected at the University of Innsbruck containing 1,500 architectural precedents, mostly 1 to 2 story houses, designed by renowned architects. Through a voxelization process, we take the models and turn them into volumetric ones at a specific resolution, some of which you can see on the right-hand side. Then, using the volumetric dataset, we developed a model called 3D voxel VQ-GAN, standing for 3D voxel vector quantized generative adversarial network that basically encodes the input houses into a predefined number of vectors or codebook embeddings and then decodes them back so as to learn the underlying pattern of house models. What is really important here is what we get after encoding, which is just a sequence of tokens, each pointing to a specific vector in the codebook as determined by their numbers. Then if we repeat this process for every house in our dataset, we basically obtain a dataset of sequence tokens, where on top of it we can train an autoregressive model like GPT, where given a set of tokens, it can iteratively predict the next one. Then let us proceed to see what we can do with these tokens. As a first mode of interaction, our pipeline enables shape interpolation to support designer in cases where they want to blend 2 different input models, probably designed by different architects, to create an intermediate inspired model. Here, given 2 such models, the pipeline encodes them into their token sequences, and when the sequences get mixed with certain strategies, we obtain a new set of tokens that when decoded, result in an output model inheriting characteristics from both inputs. More to that, our pipeline supports variation. It means that given an input model, it can refine a model and synthesize versions with varying details. Similarly, for our input, we get the tokens, and if we simply use mutation techniques to change some token values, either randomly or based on specific criteria, once they are decoded, we can get variations of our input model. And this provides us a chance, or provides the designer the chance, to generate as many number of variations as they want for each input house model. Another mode is technically called unconditional synthesis or generation, which means generating 3D house models without any explicit input information to the model. In other words, if we just sample tokens ourselves with our trained GPT transformer, it automatically samples sensible token combinations that when decoded, we can come up with new unseen house models exhibiting diverse topologies. And as a last mode of interaction, the last mode is called conditional synthesis or shape completion. It means that when the pipeline is given a partially modeled input, it can automatically understand and complete or provide suggestions for the rest of it. Here we can see the sequence of tokens that are partial, and using our trained GPT transformer, we can complete the rest and provide suggestions to the designer. Here we can see it also on another sample, and we can see how the system automatically understands the style and structure of the partial input model and provides completions for the rest. So, to conclude, this talk was about AI-driven ideation for 3D architectural design, and we have seen a range of AI methods helping the designer, not removing the designer, but helping the designer to more easily explore the design space. And as our future works, we are working to enable interoperability with downstream design pipelines, integrating semantics like materials or functional classification of building elements to our models. And also we are working on another pipeline to build it upon our existing one to add the possibility for further geometric detailization of our models. And I would like to thank my PhD advisors, Professor Wimmer and Professor Kovacic, and our team members at SB2, and also special thanks to University of Innsbruck, whom I've been closely collaborating past few months on our volumetric design project. Thank you, and thank you for your listening. I'm looking forward to your questions.
Yeah, thank you, Shevin, for this interesting talk. I'm sure there are some questions of these new strategies of early design. Yes, please.
Does the AI know already what it is doing? So does the AI know already what it is doing? So is it placing like the kitchen next to the bathroom, or is it placing the kitchen somewhere? Because we're always dealing with functions and not just random forms.
Yeah, in our first, thanks for the question. In our volumetric models, it's just at the moment it's just binary volumetric models. So it's just mostly focusing on the relation between mass and void. But so there is no specific semantics attached to the models that it can generate. But from the data set that we learn on, we filter out all the openings in the geometries. So we basically get this mass and void. And so the hope is that, and I guess we could see it on the generated synthesized samples, that it really creates a topology that the rooms, the areas, the spaces that it can create are connected to each other, so you don't often end up with just a closed area without any openings to other spaces. But this is actually our next task, to integrate semantics, to explicitly give this information to the model so it knows what space belongs to what is the functional classification of each space. Yeah.
Thank you.
Okay, further questions? Yeah, I see one down in the back.
Thank you for this very interesting presentation. I want to add up to my predecessor. I don't think it's a problem if the kitchen is in the wrong place, because maybe in those early design stages you want some kind of emergence and something to resolve later on. But my question is something else. Does it take scale into account, or is it like another question? Is it voxel based or NURBS based?
Yeah, the second, our model for volumetric design, it's voxel based. And yes, it's actually one of the, I would call it, advantages of our pipeline, that it takes scale into account, because often the generative models from the literature are trained on objects that have more simple topology, like chairs, because basically, like chairs, tables, because there exists enormous data available on them. And often when the models are trained on these objects, they do not address the scale consistency. But for us, it was one of the most important things when we initiated the project. And currently, the volume models that we generate, each side of each voxel has 75 centimeters, so we are working at this scale. And even in cases where we blend two different geometries from different two scales, the output geometry is scale consistent between them. Yeah.
Very impressive. Thanks.
Thank you.
Okay, so, one more question.
Hello, my name is Marilis Frey from Vienna, from TU Vienna. In the last few years, I worked for 2 different offices as an architect, so actually in practice. And the offices were both based in Vienna, one Delugan Meisel and one Ghana Ghana Plus. So the first one really had to do with freeform architecture in China. I was working on a project in China, and for the second one, I was working for a social housing project in Vienna. And what was the common thing was that I had 2 chefs, and actually they were both really good drawers, and I got the drawings from the chefs and had to interpret them and build up the digital models. But in one case it was the freeform architecture, in the second case it was the social housing, so really 2 different tasks. And I think actually, like, the thing that you present was that I did at my job, like interpret drawings and try to digitize them. So my question is, do you intend to, do you intend to go really out to offices? Because like, each person has its own style, its own interpretation of what is a stroke, and do you plan to go out to offices and really test this in, so to say, in real world?
Yeah, so in the first phase of our project, we, as use cases, we really focused mostly on pavilions, and but this is our goal for the next phase, to try to address also more large-scale buildings with maybe more interior in them, because in pavilions, in some of the samples that I have shown, it's just a curved surface, and so there is no really definition of interior as we do get from the rectangular shaped buildings. So yes, this is our more or less our focus for the next phase of our sub-project. Yeah.
Okay, so let's thank Sherwin again for his wonderful presentation.
Thank you.
And we are now switching the stage to the next presenter from our research topic, Advanced Computational Design. It is Lukas Lipp from the domain of visual computing, and he will give us a presentation about differentiable rendering for camera-free lighting optimization. So from the input now to the output area. Please, Lukas.
Hello, everyone. My name is Lukas Lipp, and I'm from SB4. I guess there's an error. Yeah, SB4, lighting simulation for architectural design, and I will show you how we use differentiable rendering for camera-free lighting design problems. So, lighting design, a term that refers to the strategic design of lighting setups for various environments. This can apply to theater and event stages as well as office spaces, as demonstrated in this example here. At present, this process typically involves the lighting designer making manually and iterative adjustments until the desired lighting conditions are met. On the right, we can see how this would look like with the focus on 2 office surfaces. The color overlay describes the difference to the desired target as the light is moving left and right. Of course, light usually has a very global effect on the radiance field. Therefore, this analysis can be extended to arbitrary scale. With increased scale, the manual evaluation becomes tedious and prone to errors, making automatic methods highly desirable. With recent advances in hardware-accelerated physical-based rendering and differentiable rendering, I believe we can significantly improve this process. But first, let's quickly revisit rendering and differentiable rendering. Usually we have a function, for instance the rendering function, which takes in scene parameters x and produces some output rendering y. Scene parameters can be models, lights, materials, cameras, and textures, and the rendering is usually a 2D image, like the image shown here. In the inverse case, we want to find the scene parameters that most closely represent the input image. Since it is not always easy or possible to find the inverse of a function, we can resort to the derivative of this function combined with gradient-based optimization. So let's go back to our lighting design case. Since we want to optimize the lighting on the desk surfaces of our office, it is important that the camera captures this area. What if we also want to include additional areas of our scene, such as the whiteboard? We also need to include a view capturing this part of our scene as well. Oh, and who would have guessed, there's a rabbit underneath the table, so we add another view. So the usual approach to tackle more complex targets is to add more views to the objective function. This also means as the scene scales in size or detail, the required number of needed views increases. We have seen many differentiable renderers in recent years that use images as the main way of defining the objective function. While this is the right choice for many inverse rendering problems, in the context of lighting design today, we will show you a more efficient view-independent differentiable rendering approach. As our running example, we choose to solve a complicated problem from the gaming world. Here we use a scene from a video game which relies solely on pre-calculated illumination. So the scene is quite complex with a lot of occlusions and narrow pathways, which makes it hard to capture with one or multiple camera views, which highlights the benefits of our method nicely. So this scene does not provide dynamic lighting, and all lighting is baked into so-called light maps. The combination of albedo and light map forms the final image. If we would want to recover the light positions that were used to bake these light maps, if we would want to recover the light positions that were used to bake these light maps so that we can render the scene with new visual effects, we would need quite a lot of camera views, which can be a very tedious process to create. And with our solution, this can be solved way more naturally. So the typical camera-based differentiable rendering approach works as following. Usually, each ray starts from the camera and gets traced into the scene to generate a 2D image on the image plane, also called the primer rendering, and we write this as L. For the gradient calculation, this needs to be done one additional time, but this time the ray carries the derivative of the objective function with respect to the primer rendering into the scene. Nimiot David et al. Called this the adjoint radiance, and here X marks the areas which contribute to the adjoint radiance along the path. In this case, the X can solely be found on the image plane. Our method does not define the objective function on a camera view, but instead on the scene itself. So let's start with our primer case. Since we removed the camera, a logical step is to start the rays from the light source. We then store outgoing radiance at each intersection with the scene geometry. To do this, we need a radiance cache. We need something which allows us to store radiance at different positions and in different outgoing directions. Additionally, it should be easy to project to, and also can be updated quickly. We choose hemispherical harmonics as they satisfy these requirements and are well researched in literature. They can easily be interpolated and allow for a closed form storage of radiance. The order of the hemispherical harmonics can be freely adjusted and reduced to basic non-directional RGB data when set to 0. So, in detail, when a ray intersects with a triangle, we generate some outgoing sample directions, distribute this sample radiance among the triangle vertices, and update the hemispherical harmonic coefficients of said vertices accordingly. And then the ray traversal continues. For the derivative calculation, we need to trace the scene one more time, but what happens at each intersection this time is a bit different to what happened during the primer case. Please note that we also introduce a masking parameter which allows us to reduce or turn off the contributions of different parts of the scene to the objective. So therefore the X marks are only on scene objects that contribute to the objective. So let's look at what happens to our radiance cache in the backward case. We start with taking the difference of the target illumination and the current illumination. We take the derivative of this difference and store it at each triangle vertex for later access. When we visualize this data, we can see how certain directions in the hemisphere are too dark or too bright. Violet means that the area is too bright and should be darker, while yellow means the opposite. So now let's look at what happens when the ray hits the triangle in the backward case. We gather this triangle part of the objective function from the vertices and interpolate it using the bicentric coordinate of the hit. Then we continue with our ray traversal. So high level, this looks as following. Please note that there are two parts that make up the final gradient, but don't worry, I will explain them one after the other now. And also note that for this presentation, we choose a simplified formulation. For the full details, you can, for instance, read the paper. Since our edge radiance, in contrast to camera-based versions, is distributed in the scene, marked by the X, we first need to gather this information along our traveled path and carry it to the first intersection with the scene, like happened now. So this is the first part of the final gradient equation. The second part of the equation that is missing is the direct derivative regarding our light source parameters at the first hit. Combining these two terms gives us the derivative for objective with regards to the light's parameters for this ray. So, and now we can use these gradients for our optimization. When we optimize this setup now, we can see how the bright spots shown on the hemisphere are moving towards our direction. Intuitively, this means that we want to optimize the lighting in such a way that a lot of light is reflected in a certain direction and less in others. Zooming in on one of the blobs shows this even better. Our spatial directional target allows for detailed control of where light should be scattered. Applications, for instance, in scenarios where applicable, for instance, in scenarios where workplaces need to be designed in a way that should prevent workers from being dazzled by the room's lighting, could be options. So looking back at the manual process from the beginning of the talk, we can now replace it with our automatic solution. We can now optimize the scene's lighting, consisting of one spotlight and one area light, for a uniform illumination of the desks, without the fear of missing out on any hidden areas not captured by the cameras, since our objective incorporates the entire scene. Also note that the rabbit underneath the tables gets the spotlight treatment it deserves. So let's finish our light map reconstruction example. To refresh, it would, if we would want to ray trace this scene, the provided light maps are not very useful, and we much rather would like to have the original light sources. So our goal is to approximate them using said light maps as our target. So we start this optimization with a grid of point lights. In the beginning, the lights are quite dark, and as the optimization continues, the position, color, and intensity of our lights change to match the target better. On the right, you can see the loss as the optimization progresses. Please note that we visualize all lights using an overlay which ignores occlusion. So now we can use these lights to re-render our scene using full path tracing, making use of dynamic lighting. When we look at some close-up results, we can see that the reconstruction of the lighting configuration produces a look very close to the original look produced by the light maps. One noticeable observation is that since we use the fixed amount of point lights, the number of highlights we can recover is limited by that number. Still, the overall aesthetic got captured nicely. In this example, we have a theater stage scene for which we want to find a good lighting configuration. We start by adding a spotlight and optimize it for uniform illumination of this wall. Then we add one area light and further specify the target by directly drawing on the object. We then reach our final result with another round of optimization. For the next example, we scanned in this David head in order to optimize the lighting with our tool and then bring it to the real world. The capture setting can be seen here. We used the box in which we placed the head and a small spotlight to illuminate it. So D here marks the device we used for scanning, and C, B, A are the camera, the David head, and the spotlight. So using one spotlight with some arbitrary setting, our rendering looked like this. We then sketched the desired shading directly on the David head. And through optimization, it looks like this. And through optimization, we then found the parameters for the light source that produces this result as closely as possible. And this produced this result. We then reproduced this in real life using the parameters that we calculated. And when we look at these two images, we can see that they very closely represent the sketch. And in this example, we looked at an office scene, which is hard to capture with a single image. And state-of-the-art differentiable rendering would require the placement of multiple cameras to cover all areas of interest. But there's also no guarantee that the camera placements are actually good. Since our target is basically the whole scene, we don't need to worry about this and can directly go for the optimization of our scene. So let's zoom in on the launch area in the right corner and further improve the lighting here, as we are not satisfied yet. In this case, we want a brighter illumination of the small tables here. By drawing, we can further improve our desired target and run the optimization again. And with high quality rendering, it looks then like this. So let's wrap things up. We introduced to you our global radiance cache. Then we showed you how our approach can use this radiance cache to solve inverse problems in a view-independent global manner. And finally, we showcased our solution by applying it to otherwise hard-to-solve problems. Thank you for your attention, and you can find more infos on the project page, and I'm happy to answer some questions now.
Yeah, thank you very much, Lucas, for this enlightening talk. So, other questions from the audience? Yes, please.
Thanks for your amazing presentation. Specifically in the last example, one question popped up in my mind. Like, are you considering human being and human eye in the scene for your optimization? So, for example, if you're really simulating this to use it later in installation of the lights, and the tables and objects are having a perfect exposure and perfect illuminance of whatever we need, but then the light source is installed in a way that it's not producing a very proper environment for human eye. So it's like iterating your eye when you're sitting on those sofas and you don't want to look at the table because the spotlight is hitting your eye. Are you considering that, or do you think that that could be possible in your optimization, in your process of work?
So I've shown you the example with this hemispheric harmonics, where certain directions are more illuminated and others less. You could use that already to sketch certain directions that should be brighter and darker. And for instance, if you have a sofa here, you could try to sketch it in a way. So when you move the camera to the position of the sofa, you would see how the light is reflected in that direction, and then you could draw in this direction to make it darker. Yeah. So the directional drawing interface is built in a way that, depending on how you look at something, you also draw in that direction. So what the camera here sees would also be what you're drawing at. So you could easily just make it darker.
But this is something that you have to take care as a user.
For now, yes.
It's not part of the, the automatic process.
No, not yet.
Oh, there's someone in the back. Yeah.
Thank you very much for the presentation. I was wondering if the number of light sources influences the optimization process, or how much it influences the optimization process in terms of performance.
So if you have more light sources, of course, the speed goes down a bit because you have to simulate more lights. You also run into the problem maybe that some lights just get squeezed down to zero intensity and no longer contribute. Maybe these are two problems. Yeah, I think there are multiple future works for this, so you could morph light sources or split them depending on that. Maybe one thing that is a bit of a technical detail. So in our system, you can set how many rays you shoot from each light source. And if you have more light sources in your scene, you would want to reduce this. So if you have 2 light sources, you don't shoot 1,000 rays per light. If you have 100 light sources, you don't want to shoot 1,000 rays maybe per light. This is one thing. And in general, global illumination is a very sensitive part of the rendering. So when one light source moves, basically everything changes, which makes it, I would say, in general, a bit harder compared to maybe other optimization problems like just texture optimization or roughness of some material or so.
Okay. I think it's time to thank Lucas again for his presentation. Yeah, and because there is some time left, we can also present some preliminary research results. The results are from a project called the materialization of meshes with spherical faces. We already heard in the morning session by Helmut Pottmann that the creation of spherical faces on meshes are a very important topic. And we will show you some of these results conducted by the members of the team of Advanced Computational Design. Let's start with the motivation. We saw that in architectural history, spherical structures of buildings are very important. We have here 3 important buildings: the Pantheon in Rome, in Italy, the Karlskirche just around the corner, and the Hagia Sophia. They have all kind of spherical structures. So domes and spherical structures are really very important in architecture. So now let's come to the research question. Is it possible to materialize meshes with spherical faces? Is this really possible? And some of the previous work we have been introduced today already by Helmut Pottmann. And there are 2 significant papers. One is also from our group, Martin Kilian et al., in collaboration with Helmut, and Anthony Ramos, if I spell it correctly, also contributed with a significant contribution. So here you see how this actually takes place. On the left side, you see how curves are approximated, and the usual sequence is to approximate it with some linear segments. If we want to approximate the same curve with circular segments, there are several options, and you can see how this actually takes place. In the case of surfaces, this is a little bit more complicated, and we see one example of such a mesh, where on each mesh segment we are generating spheres. So the edges get converted into circular shapes, and we have some parts of spheres that actually cover this part. As we have heard in the morning, it's rather a very complicated topic that involves higher geometry. And since we are an interdisciplinary team, we needed a proof that can be communicated to all members of our team. And after some research, we came up with a very simple proof that could be applied. The proof is actually in the pudding, as is a common word. And we actually analyzed how this came to be in the history of mathematical proofs. It turned out that the first statement of this originates already from 1605 by William Camden. All the proof of a pudding is in the eating. So we actually learned that it's a little bit misunderstood. The proof is not in the pudding, it's actually in eating the pudding. Yeah, so it's a very important fact. And we also did some further analysis of these statements, of the semantics, and we discovered that the pudding could actually be replaced by a cake without validating or invalidating the proof. So we will continue with the cake, or the proof is in the cake. And this leads us to the generation of an experiment. Experiment was done by creating spherical mesh structures in the shape of a cake. What you see here is a shape that was generated by Christian Müller, an expert in this discipline, and the realization was done by Milena Starbridge, also an expert in her field. The cake consists of several layers, as you can see here, and in the sense of a true architectural section. It has its foundation, the crunchy base. It has some connecting and insulation part, and it has also some topping. Here you can see some more detailed representation consisting of these several layered cakes. The realization, the so-called computational cake design, required several digital production techniques, mainly in producing several molds from the input mesh, some of the side walls, top covers, base forms, and so on, and of course the final baking process. Here you see the generation of the silicon mold, and probably Helmut will recognize the shape from the publication. So this was the approach to create the cake in the real sense. Unfortunately, as in the real experimental world, some things go always wrong. And one of the things that happened was in the baking process, also the mold was actually melting. So Milena had to redo the baking again. The second, in architecture, the aesthetics is very important. And you can see on the right side, the image was done with some blueberries. And it turned out the color effect was not the desired one. So also the ingredients had to be replaced. Here you see now the final ingredients. And instead of blueberries, Milena replaced them with mangoes, which really created a very beautiful yellow covering. On the right side, you see some of the sequences in this production process. So here, again, you can see how the layering took place. And at the end, we come to the final result and to the final conclusion. You might have guessed it, maybe, that the creation of the cake leads to our celebration of the 10 years anniversary. And as we know, the proof is in the cake. So we would like to ask Helmut to make the verification process.
This is fantastic. I can hardly believe it. But I'm totally surprised. This is a huge surprise that they bake such a cake under these difficult circumstances. Yeah. Several efforts. It goes beyond our paper because it's a multi-layer structure. Right? This is much more complicated. It has a base. It goes really beyond. And I just can thank you all for continuing what I had started 10 years ago. I think the start was a lot easier because at the beginning it's always easier, but then you add more, and it is really impressive how much you could add already. And I wish you all that you continue like this, add even more, get even more funding, get even more results, and 10 more years, yeah, but then you retire already, right? Okay, yeah, thank you very much, but we know the proof is in the eating. Yeah, exactly. Right, yeah, so, but yeah, we cannot all try it. No, not for me. No. I will also try. Yes, thank you very much. Thank you.
Okay, so thank you very all, and it's now not only the coffee break, it's the celebration break, so everybody should get a glass of champagne so we can celebrate the 10 years anniversary.
Yes, please celebrate with us. Drink to 10 years of GCD and drink to Helmut's great achievements.